This is Angela Galloway, and this is Math 146. We are still in 12.3 for this lecture video. The first part of 12.3 was on standard deviation. I covered that in part 1 of this lesson, but for part 2, we're going to look more into how our data is dispersed. Okay, so we're looking still at measures of dispersion. And so one of the ways to measure dispersion or how dispersed the data is to look at the range, right? The next thing was to look at the standard deviation. After that, we're going to look more at where our observations fall in the distribution. So do they fall close to the mean, or do they fall far away from the mean? One important term that we're going to start looking at and talking about is outliers. Outliers are observations that fall outside the overall pattern of the data. Okay, so let me try to create a histogram here. Okay, so if I've got a histogram like this, all right, and I'll look at it, I kind of see this symmetric shape here, but I do have this one bar over here that's kind of different from this side. Now, would this be considered an outlier? Probably not, right? But what about if it was right over here? Is that an outlier? So some of you may have said yes, some may say no. Well, if that's not an outlier, is this an outlier? If one was over here, if we had an observation over there? What we're going to have to do here is try to decide at what point does something become an outlier. Because if we don't make any distinction, then if we just say that an outlier is something that falls outside the overall pattern of the data, then this could be an outlier, or this, or all of them, or none of them. Okay, so we need to determine at what point does something become an outlier. So what we're looking at here is we want to figure out where can I put whoops, let me change this real quick. Where can I create like a cutoff point that anything that falls before this line is just a high observation. Anything that falls after this line is... So we're trying to figure out, where would this cutoff point be to figure out where an outlier is so that we all have the same interpretation of what an outlier is going to be. Okay, so one way we can look at that is, for something to be an outlier, it needs to fall outside the overall pattern of the data. So let's try to figure out where most of the data falls. Okay, and so what we've noticed is that almost all of the data in most distributions can be found within 3 standard deviations of the mean. So what does almost all mean? How do we define almost all? Well, one way to define almost all is using the empirical rule, okay? The empirical rule is a very important rule that we use only for distributions that are roughly bell-shaped, okay? So bell-shaped means that what we've kind of been looking at most of the time, when you can kind of fit a curve somewhat like that over top of our histogram. So they're going to be symmetric data sets. They're going to look something like this, okay? And so that curve ends up looking somewhat like a bell, okay? And so we call that a bell-shaped symmetric distribution, or roughly bell-shaped. It might have an extra bar over here or something like that, but roughly it's bell-shaped, okay? If our data looks like that, then we can say about 68% of our data is within 1 standard deviation of the mean. Okay, 68%. Within 2 standard deviations, we have 95% of our data. And then within 3 standard deviations, we have 99.7%. So if we're looking at a symmetric distribution, that almost all means 99.7% of the data. So what we're saying is if we find an observation that falls more than 3 standard deviations away from the mean, then that's very unusual to happen, right? That's only going to happen about 0.3% of the time in a regular distribution. So if we do get an observation that falls out that far from the mean, then it's most likely that we would call that an outlier, okay? And so that's how we're going to define what an outlier is. All right, so let's look at some examples, okay? So this is how you would work out some examples using that empirical rule. The average height of American women 20 years and older is 63.8 inches with a standard deviation of 2.2. Okay, so from that we get our mean and our standard deviation, okay? Uh, those will have to be given to you in your homework, okay? If you're working on a problem like this, they have to give you the mean and the standard deviation. Now notice that these are parameters, right? We're using mu and sigma here. That's because we're talking about all American women 20 years and older, okay? So we're talking about what the height is for all American women, or what they've based it off of. I don't know how they get this data, but however they get it, they get, you know, the average height of an American woman. So the mu is equal to 63.8, sigma is equal to 2.2. Sorry, that line's kind of crazy there, but these are just equal signs. Okay, so sigma equals 2.2. Now, assuming this distribution is bell-shaped, which it is, it looks something like this. Okay, in what range do 95% of all American women's heights fall? Well, usually what I do with these when I know I'm working with the empirical rule, I go ahead and fill out this chart. Okay, so I know that the mean is going to be right in the center, right? So my mean here was 63.8. Then what I'm going to do is I'm going to add the standard deviation 3 times and then subtract the standard deviation 3 times to the mean. The reason why I only do 3 is because the empirical rule only gives us these percentages for 1, 2, and 3 standard deviations away. Okay, after that point, there's not much of our data after 3 standard deviations away, so we typically aren't doing very much after that point. Anything that kind of falls out here is considered an outlier. Okay, so in what range do 95% of all American women's heights fall? Well, if I've already figured out these numbers using my mean and my standard deviation of 2.2, I go up here and I say, well, 95% is 2 standard deviations away, right? When I subtracted 2 standard deviations, I got 59.4, so that's the low number. The high number is 68.2. That's when I take the mean and add 2 times the standard deviation. I get 68.2. So 95% of all American women are between 59.4 and 68.2 inches tall. All right. Now, how tall are the tallest 2.5% of American women? When we first look at this, you know, we say, well, 2.5% is not one of these percentages up here, right? So how do I use this rule to figure out the upper 2.5%? Well, we need to use 2 facts about this symmetric bell-shaped distribution. First of all, underneath this curve, okay, so if I filled in all of this curve here, underneath there is 100% of my data. Okay, so all of it is somewhere. Even if you have a really short person or a really tall person, they're somewhere under these lines that extend on forever. Okay, so everybody is included somewhere under here. So that means 100% of the data is in this curve, okay? The next rule that we need to know is that because this is a symmetric bell-shaped distribution, symmetric means that what's on one side is also on the other. So the mean is also equal to the median, and it cuts this distribution in half. So I have half on that side and half on this side, okay? So we're going to use those 2 rules along with the empirical rule to be able to solve this. Okay, if I look at the 95% range, if I have 95% inside of this white area, how much is left in the red areas? So how much is not in this white area? Well, if we know there's 100% of the data total, we would do 100 minus 95, and that would leave us with 5% that is not in this white area, right? Now that 5% is going to be distributed evenly into both of the red tails. That's because this is a symmetric distribution. So if we didn't know it was symmetric and I had 5% left over, then I could say, well, I don't know if there's 4% here and 1 here or 2 and 3, or, I could distribute that 5% differently. But since we know this is symmetric, whatever's on one side has to be on the other side, okay? So if there's 5% total left over, okay, after the 95%, then that 5% is evenly distributed into both tails. So I end up with 2.5 over here and 2.5 over there. Now, if I want to know the tallest 2.5%, am I looking at this lower red tail or this upper red tail? Well, I'm looking at the upper red tail, right? Because these are the tallest women over here. These would be the shortest, right? So I'm looking at the tallest. The tallest 2.5% of American women are at this point or greater, right? Or more here. Go on forever. So they go from 68.2 inches or more or taller, right? So the tallest 2.5% of American women are 68.2 inches or taller. All right, and so that's how we would figure that out. So your homework questions should ask you about 68%, 95%, 99.7%, okay, for the empirical rule. Or they could ask about some of this leftover, the leftover tails here or here that you could figure out using these middle percentages, okay? All right, so I guess we'll end that in this one here, even though it's a short one, but that was just to cover the end of 12.3. We will get into 12.4 next time. If you have any questions, email me at angela.galloway@kctcs.edu.